Hello, I'm Michael Robinson, and I would like to tell you today about data model consistency in dynamics and system signals with a focus on some applications to control theory. Before we get started, I'd like to thank the organizers for putting together what is a very interesting and somewhat comprehensive session on topological signal processing. I'd like to acknowledge the help of quite a large group of people that have helped me on this general project. Actually, it was several different projects over the years, a number of students and collaborators, as well as various funding agencies. The key points that I'd like to communicate to you in this talk is that given the fact that a discrete time dynamical system is a self-map on a topological space of states, that you can think of this as being a dynamical system running on the global sections of a sheaf. Essentially, the idea is that the state space is encapsulated as those global sections. Why might you want to do this? Well, this talk focuses on composite systems, systems that can be broken down into various subsystems, and the sheaf can help you keep track of how the different subsystems interact. And so you could answer questions about locality. If I start out with a dynamical system and I have a state space, I can ask, is a certain decomposition into subsystems reasonable or not? Engineers often think about building up a system by way of composing subsystems. Well, this is kind of the opposite question. If I'm handed a system, can I take it apart into subsystems that are meaningful somehow? And the second question that I'd like to talk about is robustness. How well can you control or monitor this dynamical system that's built up of various subsystems under imperfect state estimation? So let's focus on locality first. This lives in the world of diagrammatic modeling. Although I'm focusing primarily on discrete time dynamical systems in this talk here, it works perfectly well for continuous time dynamical systems, as shown on this slide. The general idea is that the variables that make up your state can be represented diagrammatically, and you can learn some things about the topology of that diagram. When we're talking about these diagrams, they're built up by way of a topological space. They typically are finite topological spaces because you have finitely many state variables. And how do you build finite topological spaces? Well, there's a nice way to think about them in terms of partial orders. If you think about a partial order, you can put a natural topology on it called the Alexandrov topology. Here is a partial order on the slide, and the way that you make the open sets in this topology is by taking unions of upwardly closed sets, or upsets. So here I've marked in red one particular node and taken a look at all of the nodes that follow it or are larger than it in the partial order. That's an open set. Here's another open set. And as it happens, intersections are also open sets. That's pretty easy to see. So that forms a topology. Well, what's a sheaf on this? Well, you take each element in your partial order, assign to it a set of values for the variables that are there. These are called the stalks. You can think of them as local state spaces. They can be measure spaces, so you can handle stochastic data. And it's worth noting that the types matter. What I'm going to build on this slide is a sheaf of vector spaces. Each of the stalks here are vector spaces. And they're on a partial order. The various state spaces are related to one another by way of restriction functions. These restriction functions ought to be compatible with the state spaces. Here they're vector spaces and linear maps. These are called restrictions because they go from big up sets to smaller ones. And the main criterion is that composition needs to be path independent, i.e. the diagram must commute. If you do this, you have a sheaf on a partial order. If you think about this for a moment and have seen some other definitions, you may say, wait, this is a pre-sheaf? But actually I've only specified the stalks on some of the open sets, some of the sets of sections, as it were. And so merely what I've given you is a minimal specification for a sheaf. Now, what's an assignment? An assignment is a selection of some values on some of the open sets. Here's an assignment on all of the open sets. Essentially, you can think of this as a snapshot of the values of the state of your dynamical system at some particular time. A global section is an assignment that's consistent with the restrictions. So if you compose restrictions as you move around. Say if you start at the bottom of the diagram, there's a 2, 3 vector. If you move directly up, there's a -2, -3, -1 vector. But if you go, say, off to the left and then to the right, doing matrix multiplications as you go, you will find that you've got the same value. If you could do this everywhere in the diagram, you have a global section. You can think of this as a consistently defined way of choosing a local state everywhere that gives rise to a unique and unambiguous global state. So let's bring this back to dynamical systems. A discrete time dynamical system is just a self-map on a state space. For instance, you can think of it as a self-diffeomorphism or homeomorphism or whatever kind of isomorphism you want on your state space. As far as I'm concerned, I typically think of state spaces as manifolds, but they don't have to be. Okay, well, if I'm going to do some kind of subsystem decomposition, think of this as a networked dynamical system. The state variables are kind of localized to different parts of a graph. So this is probably good to write down what that subsystem graph is. Here's one possibility. The interpretation here is that each vertex describes a subsystem, each edge describes a connection between subsystems, i.e. shared variables that are communicated. So part of the state of subsystem A and subsystem B are shared, and they're shared by the variables that are going to end up on C. How do I put this into the sheaf context that I just showed you? Well, I want to topologize this first. So I think about a graph. Well, a graph is not quite a topological space, although by way of this Alexandrov topology, it does determine one. You make a partial order in which every point in that partial order, every element, comes from either a vertex or an edge. There are essentially two types. And you set an order relation that the edges are bigger than their endpoints. Slightly confusingly here on the slide, the edge is below, even though it is above in the partial order. Or rather, it is drawn below. Okay, so that gives me a partial order, and thereby gives me a topology. Great, so now that's just the connectivity. I need to also ascribe the variables. If I ascribe the spaces of variables, I now have a sheaf. This is a theorem. You can always do this, and the sheaf that you end up with has its global sections, or all the possible system-wide consistent unambiguous states. And the basic idea is you just label all the subsystems in your partial order with their state variables. Great. Okay. Now, what about the dynamical system part? That was just like the state of the system. The dynamical system acts on the global sections. So that's a map on the top of this diagram. I need to ask, well, okay, great. What happens on the smaller side, on each of those local subsystems? Does it induce dynamics on those subsystems states, i.e., I get lots of little dynamical systems, and the whole works as a commutative diagram. This defines a sheaf endomorphism, and the question is, when can this happen? It obviously can't always happen. If you choose a poor subsystem decomposition, this might not happen. So that's the main question. It turns out there's a very nice, crisp answer that I've proven called a sheaf dynamics theorem. It starts out with a sheaf and a diffeomorphism on the space of global sections. And what the theorem says is that given this data, there always exists, a sheaf, possibly different sheaf than the one you started with, that has the same sections as S, but might have some more. And you get a sheaf morphism that induces your original diffeomorphism. Okay. And this R is really the minimal best choice that satisfies a nice universal property. So you can conclude, based on this theorem, that you end up with endomorphisms, i.e. the local dynamics get induced by the global dynamics, if and only if the sheaf R that this theorem constructs is isomorphic to the sheaf you started with. And, well, that's kind of interesting. How does the proof go? Well, it's basically a lot of diagram chases with one snazzy tool from category theory called pushout. If you start out the solid arrows of the data we started with, the global sections of the dynamical system on the top, and on the left is the restriction map in the sheaf from the subsystem decomposition. And because each of these are manifolds, there is a well-defined pushout, R of U, with the dotted line maps getting induced. Great. And the point of the matter is that you can construct the restrictions of the R sheaf by way of more pushouts and a universal property on them. And basically you turn the crank. There's a bunch of technical details to verify that this resulting object is in fact a sheaf, not just a pre-sheaf, and that it has the universal property. In brief, it's a lot of diagram chases. They're not particularly difficult once you get started. Okay, the interpretation of this, though, is rather interesting. It says that the global dynamics induces the local dynamics only if those subsystems make sense, and make sense in a dynamically reasonable sense. Not every subsystem decomposition makes sense dynamically, i.e., you may ask for variables that get spread across the system if you have chosen what constitutes a subsystem incorrectly. Now, I have to say that engineers, since they typically build from subsystems up to a full system, they tend to build dynamically meaningful decompositions as a matter of course. And furthermore, when they are debugging problems, they're trained to intuit this idea. But this sheaf dynamics theorem formalizes this criterion to a very, very nice, crisp isomorphism. Can you get around the criterion? Always induce local dynamics by way of something like stochastic or non-deterministic modeling? Well, the answer is no, but it's a little more subtle than just simply no. While you can always induce stochastic maps on subsystem states, even if those subsystems make absolutely no sense at all, the resulting maps don't respect composition, which is to say that the resulting induction, so to speak, of course you can't see me right now, but I'm putting scare quotes on the word induction there, it's not functorial. And what this means is, that you end up with the dependence on how you actually run the dynamics. And that's sort of weird, and that's problematic. I don't know if there's a way around this in some other direction, so there were a lot of open questions around this. Okay, well, let's talk about robustness. We've got our subsystem decomposition. We've got some dynamics. We want to model and or control that system, or monitor and or control that system. See what it does. Okay, well, we need to handle the fact that there may be some errors, i.e. we've chosen a poor model or we've made some errors in observation. Okay, well, an assignment need not be a global section. It might be, like what's on the slide now, inconsistent somehow. For instance, if you start with that 2, 3 on the bottom and go to the left by way of matrix multiplying with the 1, -1, you get -1, not +1. So this is an inconsistency. And there are various other inconsistencies in this diagram as well. You can measure the amount of inconsistency that is present by way of a quantity called the consistency radius. Basically, you aggregate the distances that you get between the data that are present in the assignment and the data that has been propagated from other parts of the assignment. There are lots of restrictions you need to check in general. This is a little bit of a computationally time-consuming task, but it can be done. You can aggregate this using whatever norm you happen to want, for instance, a max norm or an LP norm or something else. It's worth noting also that I've been teased for choosing this consistency radius term. Perhaps it's better to think of it as inconsistency radius. Perhaps. Fair point. The point is that if consistency radius is 0, that's what global sections are. If everything inside is a metric space, then that's on the nose. If there's pseudo-metric space, not so much. Okay, well, the theorem that we want to make use of here is one that is an encoding of a controlled discrete time dynamical system. So if we started out with that sheaf diagram, we had our sheaf endomorphism that we constructed in the previous section of this talk. That's the evolution arrow there. S1, S2, S3 are sheaves. Great. If that were to be our dynamical system, we'd just go forward. However, if we have some control variables that are present, they enlarge temporarily one of those time states. The S2 state has not only the observed variables, but also the control variables. So how do you go back to a previous state? Well, you have to project out those control variables. You're only left with the observed variables. Fine. So that's how this particular theorem works. And one of the nice things about this theorem is it's quite tangible. you can see that a time series runs. I could extend this diagram to the left or to the right, forwards or backwards in time, without any particular problem. That way you can talk about the control action evolving as well. Great. I'm going to suggest that this diagram of sheaves be interpreted as a sheaf itself, sort of as a recipe for a larger sheaf. The global sections across this whole diagram are feasible time series when certain controls are applied. If you will, they're telling you exactly how the state evolves. Now, why would you want to do this? Well, the reason why you might want to do this now is because this particular diagram might not have a global section if there's some errors. Errors in evolution, i.e. the model is incorrect, or errors in observation. Now, one thing that people tend to do is they tend to look at optimal control if they have a controlled dynamical system. What are the best choices of controlled variables to achieve some particular goal? Well, the way to do this is to evaluate how well you're doing at each particular time step. So you run a cost function at each step. Now, I've got a little hat over the R. I'm assuming here the cost function is a real valued function running on the topology of the base topology of the sheaf. And the objective, the best thing you'd like, is for this to be 0. You want to minimize the cost. Well, a thing to realize here is that there are lots of R's all over this thing, so the little hat over the R is telling you that actually what I'm trying to do is check the R everywhere. The hat indicates the constant sheaf whose stalks are all R. That constant sheaf is sharing the same base topology. There's a lot of moving parts that are going on there. In any case, given this diagram now, it's pretty clear that if, in fact, I am able to achieve my objective, i.e. get a cost function of 0 here, then I'll get a global section everywhere. What this means is that I have a totally feasible time series running on the top, where it says local section here, and actually you get a section down below because my cost is actually 0 everywhere. I've achieved that optimal cost. Now, the truth of the matter is that optimal control doesn't assume you're able to hit 0, just you're able to minimize it. So if you can't actually get the optimum to 0, well, you're not going to get a section there on that lower half of the diagram. But you'll still need a section on the top half of the diagram, i.e. saying that the time series is feasible. This therefore says pretty succinctly that if you minimize the consistency radius of this diagram, you will in fact obtain optimal controls. That's pretty nice. It gives you a very clean way of expressing what optimal control is. But now what if there are errors in either the model or in the data? Well, allowing for inconsistency everywhere, i.e. dropping the constraint that the top row be a global section, very simply says you're now tolerating error throughout. And you're doing so in a very even-handed way. When you read what people write in the optimization and control theory literature, they have various ways that are a bit more ad hoc. This allows you to say, all right, fine, noisy optimal control is just the same as regular old optimal control, except that I've removed a constraint. The interesting thing that you get is if you run the optimization problem, solve the optimization problem, if you will, consistency radius across the entire diagram gives you a lower bound on the total amount of control error, as in how far are you from the optimal control, given the fact that there's some error, if you could conceivably get there. Now, there's a star next to the lower bound because there are some technical conditions. Certainly have a look at our preprint where we explain those in necessary and sufficient detail. So to wrap up, sheaves provide pretty convenient tools for understanding composite dynamical systems, those that are built up from subsystems. They tell you when a subsystem decomposition is meaningful dynamically. They give you a convenient framework for discussing optimal control when there's measurement error. There's lots of work to be done here. Do sheaves illuminate non-deterministic or stochastic models? Well, certainly stochastic and non-deterministic models can be phrased in this context by using more elaborate stalks and restrictions. But there's a lot of questions in how that works. What about continuous dynamical systems? All of these are discrete time dynamical systems. And, you know, it's still very much theoretical at this point. How well does this very simple idea of minimizing consistency radius across this sheaf diagram, how well does that perform in practice? Does it work really well, or does it need some tuning in order to become practical? With that, I'll say thank you for your attention. I hope this was an interesting direction. Lots more work to be done here. If you want to read more, there are a few references that you can have a look at up on the slide, and I hope you enjoy the rest of this particular session.